see out because I've got to write it enlargement of the in the lighting here, I can pick from a total of 7 scenes, and we've got scene 4 today. We'll try the others in the other lectures. I don't know if this is going to work, but it's actually rather touching that we've got 7 scenes to choose from, because this is I find this unit very aesthetically pleasing. It took me ages to write it. This year, I haven't just written it. Last year I have. But the downside of that is last year I could remember it dot by dot when I gave the lectures. This year, it was a year ago since I did. Do you have one of these? So you've all got the handout. I couldn't run to a cover this time. I know that you usually covers on the stuff I use, but once you've done the blue one and the red one.
Stay over here.
You've got the handout which covers all of the lectures, and that gives me that entitles me to miss things out of the lectures in the knowledge that you have the notes anyway. So the whole syllabus is in here. In fact, as ever, this is a bit like my second year stereochemistry booklet. It's imagined that you will take this with you, and that it's not just for this unit, it's what you'd refer to if you want to know about pericyclic reactions, in the same way that the red book is actually quite good for stereochemistry if you end up having to do any. So, as usual, there's a website, there's a Blackboard site with probably the best interactive web pages you will ever see for a unit in this establishment. I would say that myself, because nobody else will. When the Best on Blackboard competition comes around in a few weeks, I shall be asking you for your vote. So go and have a look at the 30412 website. Sadly, it's still got Java in it, but we're working on that. It should only make you log in once when you go to look at the Java applets. For each session, you log in the first time for security reasons. But after that, you'll be able to see all the molecular orbitals in this unit, and there are lots of them in full colour. Choose to fill your screen with them if you want. You can get inside the orbitals in that system. So interactive molecular orbitals and models, worked examples, that eventually is probably a bit passé. Now there are lots of worked examples, about 20 of them perhaps, and they're all of them with applets containing the actual orbitals, so that you can see why and how they should work. So do have a look at the website. It took so long to make, it would be sad if you missed it. There's only the one quiz at the moment, I think, and I'm not sure whether that's gone live yet, but there is a quiz to help when it comes to revision time. The books that are recommended, there's a reasonable amount in Flavin's book. The best book by far for this topic is one by Professor Ian Fleming, not to be confused with the other Ian Fleming. Lots of his books about. Ian Fleming is absolutely brilliant at writing things in the sort of language that helps you understand them, which is not, that might seem facile, but not every book you read is written from a perspective that the writer seems to want you to know what's going on. Quite a lot of things are just take it or leave it, this is how it is. Ian Fleming's books, you can feel yourself being taken along with it. And so of all the books that on molecular orbital theory and the way it impacts organic chemistry, that third one on the list, Molecular Orbitals and Organic Chemical Reactions, student edition, that's the book that you will take with you on your desert island with Shakespeare and the Bible. And your 8 grammar phone records, so you know what they are. Your 8 MP3 files. Fourth on the list of recommended reading is something called The Conservation of Orbital Symmetry. Now that is a seminal work that came out in 1969 in Anglo Vanta. And on the website, what you want, you may be able to tell this from the paper, but you can't make it happen. If you click on the DOI link, you'll get that paper to download. and it's the same as Woodward and Hoffman's book, which came out in 1970. So basically it's a free book, and I would recommend that you get that book down. Although having said that, it's got more historical significance than the way I'm going to approach this topic, because there's a lot of orbitals in this subject. And the conservation of orbital symmetry approach is probably the most thorough, but it's also in some ways the most complicated. And so I'm going to show you one of the things that Woodward and Hoffman came up with in their 1970 work, but only because it would be wrong for you not to be aware that that stuff exists. But you'll be pleased to see that what I use to explain these reactions is frontier orbital theory, which is slightly different, much simpler, disapproved of by Professor Fleming, I should say. But since it gives you the right answer, then I figure that that's what I should use in what is only a 6-lecture unit. There's only 6 lectures on this. We can't let you go out into the world not knowing about orbital symmetry, correlation, and parasitic reactions. But if you're only given 6 lectures to deal with it in, you can't especially deal with the more refined elements of the maths and the symmetry. So I'm not going to do that. I'm going to give you a working perspective on how you can look at a reaction, understand it, and predict what's going to happen if you don't know. That's what I've come in to do. So there will be some conservation of orbital symmetry, which is a very beautiful way of doing this kind of topic, but I need twice as many lectures if I was going to cover it in the same amount of detail. Now, first things first, what are pericyclic reactions? And I've attempted to define pericyclic reactions in reaction classes. You've got something on page 1 there, which is a summary of the slides. Obviously the web pages have got the same notes, but all the diagrams are in colour and some of them are hot linked to wherever they need to be hot linked. By the way, on the website, each of the lectures downloads as a PDF as well. So if you want a coloured version of this, the PDF that's online is that. These are all grayscale. So, the reactions you're used to ionic reactions. I'm classifying reactions according to reaction type in a very general way now, taking 2 steps back. And I'm looking at ionic reactions which you're used to, movement of electrons in pairs with build-up and stabilisation of charge. Most of the reactions that you've dealt with, apart from the radical ones that Dr. Whitehead has now done, and 1 or 2 other radical ones that you've seen before, most of the reactions that we do are ionic reactions. They involve electrophiles, nucleophiles, something that's electron poor, seeking out something that's electron rich, and then one thing attacks another and a new bond is formed. All of those things we've seen before, typified by SN2, SN1, nucleophilic, electrophilic sort of chemistry. That's classified as ionic organic chemistry. Radical reactions are different. They involve a stepwise redistribution of single electrons, and they're not driven by charge principles. They're driven largely by what I'm terming, you'll notice, hypovalency. That is electron deficiency, but without charge. They're not positive charges, radicals, they're neutral. But the point is that many of the atoms do not have their octet, and that's what drives the chemistry. They want that extra electron. And so you can get a radical adding to a double bond with no charge involved, but you can end up with a more stable radical, so the kinetics are involved as well, kinetics and thermodynamics. But the main difference between an ionic and radical is single electrons are redistributed, and you have little or no charge built up. Now, pericyclic reactions are different from these 2. They're a 3rd type of reaction. It's defined here. They take place as a continuous concerted reorganization of electrons via a cyclic transition structure. Right. You will see more in a diagram what that means, but basically that defines a pericyclic reaction. The rearrangement of electrons with a cyclic transition structure in which the participating molecular orbitals maintain bonding interactions throughout. So there's never a separation. The two reagents that are reacting together, they get together. There's this amazing, simple, and yet complicated redistribution of electron with a transition state where they're all involved. And then the reaction proceeds to the product, and there's been no charge build-up, no radical build-up, no pluses, no minuses, no dots. And that the bonding started and carried on from the moment that that reaction started to take place. And that's the participating MOs maintain bonding interactions throughout. The MOs of the starting materials simply smoothly evolve into the MOs of the product. So these two reagents get together, and the MOs combine, and the product is produced. And that's where the charm, if you like, of this process. Some of the diagrams I hope you find as exquisite as I have. These reactions are glorious. The glorious interaction of orbitals. The MOs of the starting material smoothly evolve into those of the product. And Woodward and Hoffman, to put an extremely long story short, came along and added to that the idea that while that's going on, orbital symmetry is conserved throughout. So every orbital in the starting material has an orbital in the product which has the same symmetry properties. And it's that symmetry component which makes it's that symmetry component of all the orbitals that makes their approach rather complex. And as you'll see, it transpires that you need only look at the frontier orbitals, the highest occupied, the lowest unoccupied, and you can get the same answer from that analysis. It's deficient in some ways for the purists, but for you and I it works fine. It tells us the product, explains the stereochemistry. Now, for pericyclic reactions, while we use curly arrows for ionic reactions, these electrons are going around in pairs, so why not? We have an arrow with a double head and we say this is what these electrons are doing. Radical reactions, we hedge our bets and have a half arrow, and the electrons go around singly. In pericyclic reactions, you will see that we still draw curly arrows, but it's much more arguable whether A, whether we should, and certainly B, whether we've got the direction right. I mean, if the electrons are redistributing, we don't really want to say categorically, we can't say categorically that they're doing so in pairs. And that these two are going here, these two are going here, and so on. It's just that we got so used to using arrows that you'll see arrows on my mechanisms, and you'll draw them on yours, but it's still not quite appropriate. And it's, in a way, that is expressed. It boils down to how do you know which way they're going. You draw a series of arrows in a clockwise direction. You could equally draw them anti-clockwise, and neither of them is wrong. It's the arrow that's the limitation, really. You'll see what I mean when you see the arrows. So, how is concertedness proven? These reactions are concerted. The two reagents get together. There's a reorganisation of electrons, and then the product is formed. And it all happens in a single transition state. How do we know that it's concerted? Now, this has troubled people for a long time. I don't think there's anybody left who argues about it, but there were lots of people who argued, if you like, play the devil's advocate, which happens a lot in science and is quite correct. Where people say, you're claiming these reactions are concerted, prove it. And that is an obligation. Well, here's some of the evidence. Exceptionally high negative entropy, so they've got a really well-organised, well-ordered transition state. That is what I will accidentally call the point of highest energy on the reaction pathway. Transition state is a term which I should discourage now. I'm supposed to use transition structure. But as I have the occasional lapse, if I say transition state, you will hear transition structure. Don't look around the ice. So TS is transition structure. They're unaffected by solvent polarity. That's a sure sign that we haven't got charge build-up, and that the nature of the solvent has got nothing to do with the reaction. Those bitter ionic intermediates. Otherwise, the reaction would go faster in a polar solvent, and they don't. Dienophiles, I'll define that later with 4 acceptor groups react faster than would be predicted for a stepwise process. So there are electronic, basically that's number 2 again. There's the rate of acceleration by adding acceptor groups to the part of the system that's receiving electron density is uncommonly high. It's higher than can be explained by a stepwise process with negatively charged intermediates. And finally, they obey the rules predicted for synchronous bonding processes based on frontier molecular orbital arguments, which is what I'm going to use throughout the 6 lectures to show how to interpret these reactions. And they show the stereoselectivity that's also predicted on the basis of FMO. So there are some of these reactions are extraordinarily stereoselective, completely stereoselective in many cases, and that stereoselectivity is predictable using frontier molecular orbitals, their structures and symmetry. So there's plenty of evidence that these reactions are completely concerted rearrangements of electricity. But don't forget, there are degrees of concertedness in the same way that there are degrees of SN1, SN2, pre-organisation bonding, ion pairing. There are all sorts of subtleties that may lie behind this. So it's not completely simple, but take my word for it that there's enough evidence that these things are properly proven to be concerted. All the crossover experiments and all of the stereoselectivity experiments have all been done, and it's repeatedly been shown that they're consistent with synchronous concerted processes. So let's just briefly look at them. We're going to look at them in more detail, starting with lecture 2, but this is just an introduction. So this would seem to go by rather quickly. I want to make certain points about them today, but expand on them in later lectures. The first one, cycloadditions. These are when 2 pi components combine to generate a new ring. And there are all sorts of ways that you might imagine that happening. I've drawn one here which is called a 4+2 cycloaddition. This is the original Diels-Alder reaction. I don't know, you may have done one in the lab already. What you're seeing on these introductory slides is just the terminology as well as the illustration. So 4+2, you can see that this is a 4 pi component. It's reacting with a 2 pi component. And so we call that a 4+2 cycloaddition, and there's a nomenclature of that sort for each type of reaction. There's the red arrows which indicate that you can get away with drawing arrows on this, but I've drawn them all going anti-clockwise, and you could just as well draw them clockwise and nobody could argue with you. So the arrow itself is a limitation. It's something that we're used to, and that might make us feel a bit better. It does express the rearrangement, but don't be fooled into thinking that pair of electrons has to be going that way. It could be going the other way. They're just cycling. It's a bit like choosing the direction of arrows when you redraw benzene. The other ones move around one. It doesn't really matter which way you draw the arrows. This is a thermal process, and you'll see today that the energy supply is important. An important determinant of which product you get is determined by which energy type you put into the reaction. Here's the typical diagram which shows the closed orbital loop of electrons that are not quite bonded, but we've got a new sigma bond forming here and a new sigma bond forming here. There's driving force for you, new sigma bonds and pi bonds. And so that's an explanation of why these things go forwards. New sigma bonds create a load of energy gain, so enthalpically favoured. This pi system's rearranging, that's becoming a double bond, that's becoming single, and so there are some bonds that are coming, some that are going, and it's generally expressed as a sort of series of dotted lines. And the key to pericyclic reactions is that set of dotted lines is always cyclic. It's always a loop. That's what defines pericyclic reaction. The loop of bonds coming and going like that. When that reaction's finished, what we have, notice, is the cis product only, so that the stereochemistry in the original dienophile, this 2 pi component, That's retained. That's one piece of evidence that this is a concerted process. If it was stepwise, you would not see why the cis there would give you cis here. It might give you some trans as well. So that's an important piece of the evidence for concertedness. If you have a trans alkene to start with, then you get the trans product in at the end of the reaction. And so there's one of the fundamental pieces of evidence that this is concerted. There's no crossover. Start with a trans arrangement and get that in the product, it's maintained. So these bonds are all being formed at the same time, and there's no way rotations can occur. So that's a 4 + 2 cycloaddition, formation of 2 sigma bonds from stereospecific. A lot of reaction fuel, very simple reaction, discovered in the late 1920s. These guys got Nobel Prizes for it later on, I think. I can't remember when, 40s? Perhaps the 50s. Diels and older. You've got pictures of them in the notes somewhere. Electrocyclic reactions. You may not have met electrocyclic reactions. A ring is opened or closed through the conversion of a sigma bond into a pi bond, or the reverse. Nice and vague. Here's an example, ring opening of a cyclobutene. Again, I've used arrows here, but it's even more dodgy to use arrows in this circumstance. But that does show the rearrangement of the electrons. Here we have effectively a pi bond interacting with a sigma bond, and we're starting out with a pi and a sigma, and we're ending up with 2 pi. So we've got 4 electrons that are rearranging, but they started out as a pi bond and a sigma bond, they're becoming 2 pi bonds. So sigma bonds can be involved in these reactions. If the orbitals can line up properly, that's okay. We heat this. If there's a cis arrangement of the 2 groups X and Y, then we always get an EZ product. We never get EE or ZZ. And that is an orbital symmetry-based selection rule. We'll see that in action in later weeks. Once again, there's the closed orbital loop, which is the transition state that typifies a pericyclic reaction. And those are superb reactions. You just heat it, no solvent, no reagents, just warm it up. My kind of chemistry. This is a sigmatropic rearrangement. Slightly more complicated, but the same thing. Look, we've got a sigma bond involved and 2 pi bonds. That's what they're doing. There's the cyclic array of the transition structure. It's a closed orbital loop, so it's truly a pericyclic reaction. There's an oxygen involved, that doesn't matter. When it's finished, we have this, which looks nothing like the starting material. Extraordinary reaction, useful in synthesis, making this kind of compound with a double bond in the alpha, beta, gamma delta position relative to a carbonate. Very useful piece of chemistry. But it does take a lot of imagination to look at that and think, I want to make this, I know I'll make it from one of these. It's quite a step. But obviously familiarity with the reaction is required. This is called the Claisen rearrangement because of the guy that invented it. It's called a 3-3 sigmatropic shift, and there's a nomenclature arises from the point of reaction of each of the 2 pieces. Now this is visibly 2 pieces. You can see that more better here, look. There's the top piece and the bottom piece as I've drawn it. The sigma bond that's breaking is the one that joins the 2 pieces. And there's always a nomenclature based on the relationship between where the new bond is relative to where the old one broke. So if it's a 3 atom shift from there to there, that's a 3 component. The other one is a 3 atom shift, 1, 2, 3, that's a 3 component. So that type of rearrangement is called a 3-3 sigmatropic rearrangement. You'll see lots of 1N systems, 3 3s. There are some which are very common and others which are quite rare. And so you'll see that's a common one, 3-3. Sigma bond appears to move across a conjugated system, so that sigma bond appears to go from there to there, but that's a very rough approximation to how it does it. Now, if I can summarise these cartoons, this is an attempt again, to make life simpler by having categories that you can immediately, I hope, see these reactions in. Pericyclic reactions concerted, they're reversible, that's important. You'll see that there are certain mechanisms which are quite difficult to deal with in the forward sense, and a whole lot easier to understand if you just look at the reverse reaction. And since these reactions are all reversible, that's legitimate. So ring opening of cyclobutene, you can analyse the reaction from the point of view of ring closing of the diene, and that's still valid, it still works, it gives you the same answer, even though the reaction actually goes the other way. So it's that reversibility we can tap into it and use it to interpret. So these are cartoons. Look, we've got an appropriate conjugated pi system. A sigma bond is in red. In an N plus M cycloaddition, we're making 2 sigma bonds from a system like that and a system like this. They're the 2 sigma bonds, cycloaddition. In an electrocyclic, we're making 1 sigma bond from out of the pi electrons. Or we might be opening the system and making the diene, making a pi bond from a sigma bond, reversible. And in an NM sigma tropic rearrangement, we've got this arrangement. We've got a 1 to N pi system joined to a 1 to M pi system, and we're joining the ends that are N and M. And that's what gives us this nomenclature, the NM sigma tropic rearrangement. We treat this one with V3. So you're going to see all types. I'm going to illustrate all of these and show you the basic fundamental orbital interactions. But that's key. Forward or reverse reactions provide the same analysis, so we can use whichever one is the most convenient. And I will do that unashamedly. The typical reaction profile is the same as the SM2. It's a typical concerted reaction profile. Transition structure. And they are, just like most reactions, they are driven by thermodynamics. Heading to a more stable arrangement, that's what drives them. B more stable than A, it will go towards B. If A is more stable than B, it will go the other way. And they can do that, go either way. Now, it's very important, you will immediately appreciate, in fact, that the way that since the orbitals involved in dictating the way these reactions proceed, the occupancy of those orbitals is all important. And the source of energy that's provided determines whether or not these reactions proceed through what you and I would call a ground state orbital or an excited state orbital, and that will change the chemistry. So in this look at some of the examples, all of the numbered examples, I've numbered them because it makes it a lot easier to refer to them by number in text or in conversation. And several of them, many of them, certainly the early ones, they're all illustrated in Java applets. All the orbitals are there for you to go and inspect. So that number there often means there's an applet on the website for you to go and look at. Here's a common cycloaddition. Mode of activation, we're looking at heat or light, number of electrons involved in the transition structure. This is our analysis. Mode of activation, is it heat or light? How many electrons are involved? The count is important. There's a Huckel component to this in one of the explanations. And the stereochemistry of the starting materials and the products, that's important because we know we want to expect that it's retained because we have a concerted process. So we must choose stereochemistry for the products which provides us with the right stereochemistry. Choose it for the starting materials that provides us the stereochemistry we want in the product. And here's some examples then. These are cycloadditions. This is a 4+2, so there's a total of 6 pi electrons, 6 electrons involved. So that's a 6-electron transition state. It proceeds thermally, not photochemically. And you'll notice that the number of electrons and whether or not it's thermal or photochemical seem to change in concert, and that's no mistake, that's no accident. They do go together. If it's 6 pi, the cycloaddition will be thermal, and this is the product. There's a cis relationship between those two hydrogens, which is what they were before they reacted. And you never get the trans product. It would be too strained anyway. If you take an alkene with maleic anhydride, which is what this is called, and photolyze it, you can get a cyclobutane out of that reaction. So you get a similar sort of cycloaddition, but we're joining a 2 and a 2. That's a 2 plus 2, not a 2 plus 4. And it requires light to make it go. It's a 4-electron transition state, 2 pi bonds. So that's a 2 plus 2, and it has to be photochemical. So we've got direct difference. If we photolyze that, we don't get this product. If we thermalize this, we don't get that product. It relies on the energy source. And you'll see the orbital reasons for that when we look at it in some detail. The 4 plus 2 can go with cyclopentadiene, which is one of the more reactive dienes that do allow some simplistic versions of your chemistry into this process. Don't forget that this diene, the reason it's so reactive is because it's locked in the S-cis conformation. It's locked in the required conformation for reacting as a 4 pi unit in a cycloaddition. The double bonds cannot get away and become transoid. They're locked in that ring. So this is extremely reactive. When you do your ferrocene chemistry in that second lab, Mike has to make this stuff on the day because it dimerizes within hours. If you can't buy it, you buy this from Aldrich, you heat it to 150 and it gives you some of this, and slowly during the next few hours it recombines. And that's a manifestation of how reactive cyclopentadiene is. It's so reactive that it will react with itself. And there's one of them reacting as a 4 pi system and the other reacting as a 2 pi system. So that's a 4 plus 2 cycloaddition going on. It's effectively the dimerization mechanism. It's a 4 plus 2. 6 electrons, back to 6, and it's back to thermal. It's not photochemical. Here's an electrocyclic reaction. This is a 6 pi electrocyclic reaction. It takes 175 degrees to make it go. We have to start with EZE. Specifically, that bond there has to be Z, otherwise the ends of the chain can't meet. If it were trans, they'd be held apart. So that has to be Z. And if it's EZE, as shown there, then we get a single product, this cis dimethyl. We don't get any trans dimethyl. That's a 6 electron transition state, so it's transition structure, and it's thermal, not photochemical. 6 thermal, 4 photochemical. Published in 1973. At the time, the 70s was a rich time for this sort of chemistry. And what happened was the theory came out at the end of the 1960s. And people worked out, well, if this is true, then all these things must happen. And then they spent the 70s making those things happen, because the theory had come out predicting that they would happen. And one by one, they were shown to work. It's very nice when science works that way. So much of science, and you will have noticed perhaps, is that you observe a result and then you figure out what must have happened. Much better to sit down with the theory and say, if we do this, this should happen, and then you go in the lab and it works. That's something of a treat when that happens. More electrocyclic reactions. If we take the dimethyl cyclobutene with the cis arrangement and we heat that, we get, it was shown by these guys that you get more than 99.5% EZ, and you get less than 0.1% of EE. And those less than and more than, that's just the limits of detection. It's not that there was less than 0.1%. They couldn't see any, but their limit of detection was 0.1%. So that's, to all intents and purposes, completely selective for this EZ product. 4 electrons thermal. When you have the trans diene, you can photolyze that and the reaction goes back. So look, we're over here with the thermal reaction gives you the diene. If you photolyze the diene, it encloses. That's an interesting one. Why the light makes it go the other way. And it makes it go the other way with opposite sterochem. Look, this is the forbidden product from the thermal reaction ring opening is the EE. But if we take the EE and photolyze it, it ring closes to give that cis starting material. So that's a fine illustration of the subtlety of these reactions, all explained by the orbital approach. Sigmatropic rearrangements. This is cyclopentadiene with a methyl group added, and it's not stable, it's frustratingly unstable. You can methylate the anion of cyclopentadiene, and at first sight you get that. But you leave that at room temperature, you go and have a cup of coffee and come back and you find that the methyl group's moved round. Or has it? Actually, that's a description that's descriptive. What's happened is that the methyl group, and I've tried to draw it in my diagram, the methyl group hasn't moved around, the double bonds have. It looks like the methyl has, of course. So 5-methyl cyclopentadiene turns into 1-methyl and then 2-methyl cyclopentadiene. And you end up with an equilibrium mixture with all three. So if you make this doing cyclo additions, expecting them to go across there, that methyl group turns up in all possible points in your product. Here's another rearrangement. That's a 6-pi thermal. This is, actually it's not 6-pi, it's 4-pi and 1 sigma. 4-pi, 2 sigma electrons involved in that. I'll show you in lecture 3, I think. This is a heating and allyl ether. That's a Claisen rearrangement. It's a 3-3. Look, we're joining positions 3 away from there, 1, 2, 3, that's there. And 3 away from there, 1, 2, 3. Those positions are joining up, and that's the product we get. It's a very useful ortho-functionalization that you can do in phenolic compounds. Here's a sigmatropic rearrangement. This is a Claisen. This is an oxycoat. So it's a 1,5 diene. 1, 2, 3, 4, 5 is the relationship between them. That's the one you require for this reaction. The 1,5 relationship. 1, 2, 3, 4, 5. There's an oxygen on the sigma bond. That makes it into an oxycoat rearrangement. You can do this without the oxygen. It's just a coat. With the oxygen, it's much faster. And if you heat that at 220 and then treat it with water, you get this. And I won't spoil it by showing you the mechanism for that. It's a rather fine mechanism, and we'll see it in due course. So these are some of the guys who helped the theory to emerge. Curry and Woodward used to like a cigarette, in case you couldn't tell from the photo. That's taken in his office in the days when it was allowed to smoke. Hoffman is still going, still making videos, some great videos from him on YouTube if you're interested. These guys between them came up with the bulk of the theory. And they, as I said earlier, they did it by throwing down this gauntlet saying, look, this orbital explanation means that we can explain the few experiments that we've already done. It means all of these others have to work. And lo and behold, one by one, they're finding that they do. A lot of that work took place in the 70s. Fukui, in a way, is the main man when it comes to the frontier molecular orbital approach. There's a lot of work in the 50s on that. You'll see in a moment some of the equations involved. Woodward and Hoffman, Woodward is a synthesis guy. He was trying to make vitamin B12 at the time. He wanted to know why certain reactions were selective, completely so. And he was totally intrigued when he observed them, and he got together with Hoffman, who was a theoretical sort of Propellier type. And between them, the synthesis guy and the theory guy, they worked out what was happening and how you could exploit it. And then they wrote that paper, and that was made into a book. So these are the main people, the main human components, and they're very important, fantastic skill and scientific endeavour that they undertook to get to where we got to. Now, I'm going to use orbitals a lot, so I'm using the last 5 minutes to revise a couple of issues which I'm hoping that you're familiar with. One is you'll have to drag up all that stuff of Eric McInnes in semester 1 of year 1, how to make molecular orbitals, linear combination of atomic orbitals, and I'm going to use this sort of diagram repeatedly. Here's a CH bond. I'm taking shortcuts right, left and centre because I don't find this particularly enlightening. You know that there are more orbitals involved in these species than the ones I'm looking at, but that is the advantage of using frontier orbital theory. By and large, that basically says that if you ignore all the other orbitals, it won't really make a difference. So we're at the front end of all the orbital systems. There's our hydrogen 1s, and I've used by convention an sp3. I'm cheating already by hybridizing my carbon to give me 4 sp3 hybrid orbitals. That's just a trick, a mathematical trick, but it happens to work, okay, so I'll keep doing it. There's my sp3 orbital. I'm going to overlap it in a positive way with this hydrogen. That's our CH sigma bond, and the antibond therefore has got to look something like that. And it's the phase change that's important. I might have got the shapes wrong. I've ignored a whole load of other orbitals. Look, as it points out here, methane has 8 valence electrons and 4 MOs. I've only shown 2 here. But this is the business part of the molecule. CH sigma star, and the symmetries are in phase for a bond and out of phase for an antibond. And that's something I'm sure that is not too revolutionary. Here's a CC sigma bond, same principle. I'm combining a C2P with a C2P, and I'm making that overlap, which is positive. They're in phase. That's my sigma bond. The sigma star, they're out of phase. So I've just basically turned one of them round. It doesn't matter which phase I've turned round. So that's too should not be a revolutionary idea, but that's an in-phase overlap to give me my sigma bond, and that's the antibond. Methane has 14 valence electrons and therefore 7 filled MOs. I'm only using those 2, and that's enough. The CC pi bond, C2 pi sideways overlap C2 pi. This is higher in energy than any of the other occupied MOs of the theme, so it is truly the highest occupied orbital. Look, the HOMO, the highest occupied molecular orbital, and this pi star is the LUMO, and these are the important orbitals. That's what they look like symmetry-wise. In phase overlap, these are the atomic orbitals. The pictures that you see here are hopeless, showing what the orbital actually looks like. You've got to go onto Blackboard to see the calculated orbitals for that. But you know that there's just this area of electron density above the plane, an area below, and this is just showing you Chem-Draw's version of the atomic orbitals that contributed to it. So it's a hopeless picture. But the symmetry properties work. The plus plus minus minus, that stuff works. And don't forget these coefficients have size as well. It's called a C value. And for these two, they're both 0.71, which is 1 over root 2. And there's a little appendix in lecture 1, which, for those of you that have forgotten where that came from, you can remind yourself of this stuff. So the size of the orbitals and the phases of the orbitals are important in this whole course. But I'm only picking on the HOMO and the LUMO each time. So if we make butadiene, this is child's play now. You just take 4 C2P orbitals, then you combine them linearly. There's no nodes, 1 node in the middle, 2 nodes, 3 nodes. Perfectly simple, mathematical combination. And we occupy it into the bonding orbitals Psi1, Psi2, but we've still got Psi3, Psi4, they're anti-bonding, they're not occupied. So that's butadiene, that's the picture that we use for it. Notice the sizes. I've tried my best with Chem-Draw to show you small, large, large, small. Actually the values are 0.37, 0.6. And that can have an importance in selectivity later on. So that's why I've incorporated a few of these coordinate coefficient values. You can see the same values, but they're swapped around. The middle ones are 0.37, the outer ones there and there. But the symmetry is the all-important thing, especially with the relationship between the first one and the last one. First one and the last one. Here's allyl anion. Now this is allyl anion, it's simply 3 orbitals on the same 3 C2P orbitals. There they are. 2 from the double bond, adding to 1 on the carbon at the end with the minus charge on it. So that's got 2 electrons in it, and this is a pi bond, and we're just adding them together. We're making now 3 orbitals, and it's got the occupancy, and we've got 4 electrons in total, and it's in the first 2. So this is the HOMO. Sorry, that's the HOMO, this is the LUMO. LUMO, HOMO. And that's the symmetry. The lowest one, there's no nodes. The next one, there's 1 node. And the next one, there's 2 nodes. 0.5, 0.71, 0.5. The values that come out from the coordinates. Coefficients. Now, yes, that clock's right, isn't it? So allyl anion, it's the same, I'll finish here, that the allyl anion is the same set of orbitals to the allyl cation and the allyl radical, it's just that you've changed the occupancy. So there's the cation. We've simply taken the 2 electrons out of there, and we now have this as the HOMO, and this is the LUMO. And that change as to which is the HOMO and which is the LUMO changes the chemistry. And there's the CO pi bond. Don't forget these 2 orbitals now start off at a different place relative to each other. I'd better continue with that next time.